All right. Good morning, good afternoon, possibly good evening to those of you who are joining this webinar today. I'm very happy to have you, and I'm very happy to have our speaker, Dr. Erin Abner from the University of Kentucky ADRC, join us for this webinar. Just a couple of things before we start. This webinar will be recorded and posted to a YouTube page afterwards, after which all attendees who registered for this webinar will receive the link for it. The talk itself will be around 45 minutes with about 15 minutes for Q&A and discussion. Dr. Abner has graciously agreed to take live questions if those feel so inclined, but if you want to just submit your question via the chat, you can do that as well, and I will moderate the question for you. So I will go ahead and get started with a brief introduction here. Erin Abner is the co-leader of the Data Management and Statistics Core of the University of Kentucky Alzheimer's Disease Research Center at the Sanders Brown Center on Aging. Dr. Abner is a professor in the Department of Epidemiology and Environmental Health in the College of Public Health, where she teaches causal inference and other research methods in epidemiology and biostatistics to graduate students. Her own research focuses on the understanding of how comorbid medical conditions affect cognitive trajectories and neuropathological outcomes in life. And I'd also like to add that I have the great pleasure of co-chairing a featured research session with Dr. Abner this summer at AAIC in Amsterdam. So very happy to announce that. So with that, Erin, I will turn it over to you.
Thank you so much, Mike, and thank you to everyone who's joined us here today. I see some friends online and some potentially new friends as well, so welcome everybody. As Mike mentioned, I teach causal inference, and so I'm going to give you an introduction that sort of condenses about an entire semester's worth of material into about 45 minutes, but I think it's going to be fine. I do welcome questions as I'm talking if those occur to you. And certainly feel free to put them in the chat as well. I'm going to share my screen in the testing. There was some technical strangeness, but it worked out. So if we freeze and there's a delay, we're just going to hang in and I think it'll be fine, but hopefully it will share easily. Well, maybe not. Okay, I think we have shared successfully and that you should all be able to see. So I'm going to go into the slideshow. Okay. So causal inference and ADRD research, you know who I am and where I'm from. I want to talk about two concepts broadly, which is the potential outcomes theory of causal inference. And so I do want to make a distinction up front that there are many methods that can be used to perform causal inference, and this is just one of them. And then in addition to this introduction to the potential outcomes theory, we will talk about the target trial framework, which gives us a really nice method of implementing these methods in our research. I am taking material from this textbook called Causal Inference, What If? By Miguel Hernan and James Robbins. I cannot recommend it highly enough. If you are interested in learning more about causal inference, it's divided into 3 sections and starts with very conceptual theory building material. The writing's very accessible. If you just have a basic understanding of epidemiology and statistics, you should be able to follow along in the textbook just fine. And so again, highly recommend. So we'll start with the definition of a causal effect that we would have in the potential outcomes version of causal inference. And that is simply when we have a unit that is treated, a person we would think of, so they receive some sort of exposure, some sort of treatment, some sort of intervention, and we'll call that A, random variable A, and our outcome we'll call Y, another random variable. That is causal, that association is causal when the potential outcomes, which are represented with a superscript of A, right, with Y there, are different under different levels of the treatment. Doesn't matter how big the difference is, any difference is considered a causal effect. So this expression, right, Y superscript big A is equal to little a is not equal to Y superscript big A is not equal to little a. So with the potential outcomes when the treatment A has different levels, if those two things are not equal, that means there is a causal effect of treatment A on outcome Y. So very simply, when the potential outcomes are different, we can say that there's a causal effect. This is tricky though, right? Obviously, and individual causal effects are what we really care about in terms of health outcomes, right? What can I do personally that will change my future to one that I want to see? That's really difficult, right? If you're a fan of memes, you've probably seen the domino meme, right? Where some event is posited as the beginning of a chain of events that leads to something at the end. And sort of here, right, we're attributing trust issues in later life to things that happened in childhood. And so what makes this difficult is we can never know what would have happened in later life in terms of our trust issues if the people had not said that our shoes were untied when we were children, right? It certainly could be the case that we would still grow up to have trust issues, but for different reasons. And so it's very difficult on the individual level, if not impossible in many cases, to say that an individual exposed to a particular treatment experienced a causal effect due to that treatment. And that's the fundamental problem of causal inference, right? We can only observe one potential outcome for any individual, and that's the one that corresponds to their observed treatment. And so we can't ever evaluate that expression, right? That very simple definition of a causal effect, because we can only observe one side of it, assuming even that there are only two possible levels of A, right? A and not A. We can only observe one. And so we can never know what the individual causal effect is. So that's a problem. However, algebra swoops in and saves us because we can't estimate or we can't know the expected value of those individual causal effects, right? We can't know the average of those differences. But it turns out that the average of those differences is equal to the difference of the averages in those potential outcomes. And so if we can find a way to get valid estimates of the potential outcome under treatment A is equal to 1 versus the potential outcome when A is equal to 0, then we can start to make some causal inferences. And in the potential outcomes theory of causal inference, what we need are what we call the identifiability conditions, which I'll talk about in some detail a little bit later. But if we can assume that our identifiability conditions hold, then we can estimate the mean potential outcomes under the different levels of treatment using observed data only, right? Notice on the right-hand side there at the bottom that those are all observed data quantities. There's no superscripts for potential outcomes. So we can move from the potential outcomes space to the observed data space and make causal inferences if certain things are true, which we'll talk more about. So again, I want to emphasize what we mean by a causal effect in this framework. So traditionally in epidemiology, right, we've got people in a population. Some of those people within the population will be exposed or treated, and some of those people will be unexposed or untreated, right? Again, assuming a simple binary exposure. The paradigm of causal inference is that, again, we can't estimate individual causal effects, but we could say that if the entire population were exposed to a particular level of the treatment, and then everything else stayed the same, but simultaneously the entire population was also unexposed to the treatment, right? And those two outcomes are different, which is what we see here on the left in the figure, then we would conclude that there was a causal effect of treatment A on outcome Y. Association, on the other hand, compares the observed outcomes in the portions of the population who are treated and untreated. So fundamentally, the things that we are trying to estimate are different. Any questions at this point? Okay, great. But when is association causation? So we could think about an ideal randomized trial, right? We have a treatment that's well defined, and we need something called the stable unit treatment value assumption to hold. And this just means that the expectation is that if I, as an individual, receive a treatment, then I will always have the same outcome from that treatment. And my outcome will be the same no matter how I receive that treatment, and no matter what treatments people around me or units around me receive, right? So no one else's treatment interferes with my treatment. And that's a strong assumption. So there's certain things that do not lend themselves very well to this, like educational interventions, for example, things having to do with infectious diseases or vaccines, where other people's treatment or exposure may affect your outcome. So we have a well-defined treatment and set the holds. We want to have treatment groups that are exchangeable. And what do I mean by that? Simply the idea that in a clinical trial, right, we have some probability of treatment and we end up with some number of treatment groups, and let's say that it's 2. If our randomization procedures have been successfully applied, then it doesn't actually matter which group receives which treatment, right? If I meant to randomize group A to treatment A, but I accidentally gave them all treatment B instead, and I gave group B treatment A, on average, I would expect my trial to have the same results as if I had assigned the treatments in the way that I had intended to in the first place. So I can exchange those groups who are being treated and expect that their potential outcomes, right, are not going to be affected by which group happened to receive the treatment. And I'm making a distinction between their potential outcomes and their observed outcomes here. So exchangeability rests on the idea that our observed treatment, the treatment we receive, is independent of our potential outcomes. And I'll talk more about that later. The third thing that we want to have is that all units in the trial population, right, are eligible for all levels of treatment. So we need there to be some positive probability that all the individuals in the trial can get all the levels of treatment. Now, in a clinical trial, that's pretty easy to enforce by design. In observational data, not so much. So in this clinical trial setting, the difference in the observed outcomes, right, in the groups, we attribute to the treatment, assuming there is a difference. And the potential outcomes here, right, for group A and group B, for the treatments they didn't get, are missing by design, versus when we have observational data and the data are not missing by design, right? People get exposed for reasons that are meaningful and probably causally relevant. And so we have to account for that somehow when we're trying to use this framework. So how can we do that? So we have G methods. So G methods are a family of analysis methods, right, that are based on this potential outcomes theory of causal inference. And as I mentioned before, these rely on very strong identifiability assumptions, right? And so the big three are consistency, exchangeability, and positivity. So these correspond exactly to the 3 elements for the ideal trial that I mentioned on the previous slide. So consistency means that if a person has an observed level of treatment, so the ith individual, their treatment level is equal to little a, then their potential outcome under that treatment, y superscript little a, is equal to their observed outcome under that treatment, or y sub I. Okay, so we need the treatment to always have the same outcome when given to the same unit. And that's only possible if the treatment is really well defined, as we'll talk about more later. Exchangeability, as I just mentioned, means that the potential outcomes are independent statistically of the observed outcome. And positivity simply means that there must be a positive probability of treatment for all levels of the exposure. Bonus assumptions that we need to be aware of are what we have no model misspecification and that we have no measurement error. Again, all these extremely strong assumptions. So if we're thinking about consistency, two main components to keep in mind. One is the precise specification of the counterfactual outcomes via a detailed specification of the superscript little a. What precisely do we mean when we say that a is equal to little a? Assuming that we can define that well enough, then we can link the counterfactual outcome to the observed outcome, right? So a participant with observed treatment A is equal to little a has observed outcome Y equal to their counterfactual outcome Y superscript little a. So my observed treatment leads to my observed outcome. We assume that my observed outcome under that treatment is equal to my potential outcome under that treatment. My potential outcome under treatments that I did not receive are unknown. Those are missing. So again, with exchangeability, the potential outcomes are independent of observed treatment. And so we can see this works with randomization very easily because let's say that we have a fixed treatment probability and it's 0.5. We have 2 levels of treatment. So it must be true then that even if we conditioned on knowing potential outcomes, which we don't, if we did though, we could condition on them. But because that treatment probability is fixed, it's always 0.5 and it's 0.5 no matter what, it doesn't matter. It can't have anything to do with the potential outcome, right? Because the probability of A is always 0.5. It doesn't matter what the potential outcomes are. And by symmetry then, we can say that the potential outcomes are also independent of that treatment probability. So because of this relation, we can say it doesn't matter then which group receives which treatment because they are exchangeable. The observed treatment is independent of the potential outcomes. And again, this works by design with randomization because the treatment probability is not affected by anything that happens in the future. But as we know, probably are painfully aware, observational studies are not randomized trials. Treatment probability is not fixed. Exchangeability does not hold, but all is not lost. We have some options. So we'll never assume that exchangeability holds whenever we have observational data. That wouldn't be reasonable. But is it possible that we could learn enough about the determinants of exposure that we could achieve what we call conditional exchangeability? So conditional exchangeability says that the potential outcomes are independent of the observed treatment, conditional on covariates, right? So in this potential outcomes world, the notation that we use for L there tends to stand in for the information that is required, the minimum set of information that is required to create independence between the observed exposure and those potential outcomes. And so the expression that we looked at earlier in terms of the difference of those average potential outcomes, we can operationalize with observational data by including those covariates in L. Positivity in observational data is a little bit trickier than in a clinical trial. And again, it sounds really simple. The probability of being assigned to a particular treatment level must be greater than 0. Okay, so that's fine. However, that is not the case in observational data, right? If we're in a clinical trial, all of the participants who are being randomized have passed some screening criteria. They all meet some standard inclusion and exclusion criteria. And so they all are eligible for all levels of the treatment. But in observational data, you will have some participants or some patients or beneficiaries, whatever kind of data you're looking at, that some of those people are not eligible for some levels of the treatment. We can think about this intuitively in terms of medications, right? There's drug allergies. And so we know, for example, that, there's certain kinds of our participants who can't get an MRI because they have a contraindication to getting into the machine. So there will be some people always in observational data that essentially have this zero probability of having any exposure other than what they actually have. And those types of people create a problem for us in causal inference. And so that's something that we have to be aware of. And it's part of the framework that I'll describe in more detail in a bit. But for one of the nice things for us is in observational studies, if we can assume that we have achieved conditional exchangeability, we only need positivity to hold for the values of L that we have represented in our data. We don't need the people in our data to be able to have all possible, values for the covariates in L, just the ones that we observe in the data set. So in other words, here's the deal. We may be able to make causal inferences using observational data if we can conceive of our study as a conditionally randomized experiment. And this is where the target trial framework comes in. So what we want to do is to use the RCT that we would like to do to design our analysis of our observational data. So most of the time, the trial that we would like to do, it's not feasible, it may not be ethical. We may have to follow people for too long, it would be too big. None of that matters at this stage. We really want to think about what would the ideal RCT that could answer our question look like. So we think about this in much the same way that we would think about designing a clinical trial that we were going to conduct, right? What treatment or exposure should we compare? What outcome should we compare? And what question about the outcome do we really want to answer? Who should we include in the target trial? How long should we follow those people? And how should we design our analyses to answer the causal question? So again, very similar to designing a clinical trial that you were going to conduct, except here, it's the ideal study that you would do were it possible to answer your questions from observational data. So consider, for example, some of the risk factors that we think a lot about in ADRD research. This figure is from a 2015 review of modifiable risk factors for cognitive decline that was done by several folks from the Alzheimer's Association, right? And so there's definitely causal implications here, right? These things are increasing or decreasing risk. Would we be able to use the target trial framework to evaluate these exposures or exposures like these? And I'd say it's going to be tough. Let's talk about why. So let's say, for example, that we want to estimate the causal effect of midlife obesity on dementia risk. And I would say immediately in the potential outcomes framework, we have a problem. And that problem is the consistency violation. And so this means that in order for us to be able to estimate the causal association of midlife BMI with dementia risk, we need to be able to conceive of an intervention where we could compare the risk of dementia if everybody in the population had BMI greater than or equal to 30 versus they simultaneously also had BMI less than 30. In addition to the fact that this is obviously not possible, right? BMI changes, if they are achievable at all, happen over a long period of time, can't be randomized in a trial. It's also not clear that our exposure here, our treatment is well defined enough, right? Is it enough to say BMI greater than or equal to 30? Is every exposure the same within that category of greater than or equal to 30? And is it the same if it's less than 30? Is that homogeneous enough? And I would say, no, it's not. And again, we can't randomize people to an exposure like this. Right, so that's our definition of consistency. If the observed outcome, if the observed exposure is equal to a particular value, then the observed outcome is assumed to be the potential outcome for that exposure. And so the question we have to ask ourselves is, can we assume that the same BMI for a given individual would always result in the same outcome? Probably not. No matter how they got that BMI, whether it was genetics, it was whatever the environment, the lived environment, different outcomes are likely, right, from the same BMI, from the same individual. And then we have to ask ourselves, again, are the determinants of BMI causally relevant to the potential outcomes? And again, I would say that they are, right? Is it the fact that the BMI is what it is, or is it how the BMI came to be what it is that's relevant? So unfortunately, we're going to have similar problems with most biometric exposures. And so we want to be able to answer the question, could I assign this exposure through randomization? We need that answer to be yes, even if it would be unethical to do so in terms of like what is physically possible. Could we assign this exposure through randomization? And so things like blood glucose, for example, or blood pressure, different biomarkers, those are going to be difficult to think about estimating causal effects within this framework. Doesn't mean that they can't be causes, doesn't mean that they're not important, simply means that this framework is not the right one to deal with those exposures. So for the causal inference under potential outcomes, we need consistency, right? We need a really well-defined treatment that we have some confidence would cause the same outcome, no matter how that individual received that treatment and no matter what treatments the individuals around that person received. So we're not going to do BMI as a cause with this framework. What about something like physical activity? Could we do that? We could think about a clinical trial, and indeed there have been many clinical trials, right, where people are assigned, randomly assigned to different levels of physical activity, and we compare their outcomes. Physical activity, however, just on its face is not well defined, right? But we can make it more so. And so refining that causal question is an important part of this process. So let's say, for example, not is physical activity associated with dementia risk, but let's say we want to be really specific and say that we want to estimate the causal effect of performing 2.5 hours, right, of aerobic exercise per week on dementia risk. And we want that exercise to begin at age 45. So now I have described a really specific exposure, one that would be probably difficult to impose on the population, but not physically impossible. And that's fine. Okay, so now I have a level of exposure that I'm interested in, but compared to what, right? What would be the other arms of my randomized trial? It might be slightly less amount of physical activity per week. It might be no activity per week, right? A lot of physical activity per week, or maybe the same amount of time of doing a different type of exercise, weight training, for example. So we have to define not just the treatment that we're interested in, but the not that level as well. And there could be more than two, obviously, right? This can extend, but we have to precisely define everything that we intend to evaluate as a level of treatment. And then we move on to who would be included. And so we would want to exclude people, for example, who are not going to be able to do 2.5 hours of aerobic exercise per week. It wouldn't make sense to include them. We would want to include people perhaps who had never been active, physically active. Maybe these are people who have been pretty sedentary over their lifetime, and now we want them to start exercising. What does that look like? Or maybe we only want people who have been generally active, right, up until the age of 45, and now we're going to give them this really strict exercise regimen. and see what happens. So we really want to think carefully about who the population of interest is for our causal question. And those are the people that we would want to include in our target trial. And then we have to think about how long will we follow the people in the study. And just for argument's sake, we can say here that we should follow them until age 85 if we want to observe, dementia cases. So the target trial is not feasible. The advantage, however, is that it gives us a really clear framework about how to approach observational data sets that we would need. Like, what would we need to know? What would we need to have in the data in order to estimate this causal effect? We would obviously find, oh gosh, there aren't any existing observational data sets that have, adults starting at age 45 and they do this thing, right? They start exercising and we have all of these data. So then you start loosening those things until you can get to what you can do with the data and still match the intention of this target trial that you're designing. And then so let's say that we have a good sense of what our target trial is going to look like. Now we need to figure out how we're going to do our analysis. And I want to turn our attention now to the concepts of estimand, estimator, and estimate. So our causal question here is, what would be the difference in population, again, not individual, population dementia risk, if the entire population of age 45 adults began exercising 2.5 hours per week until age 85, compared to if that same population did not get any exercise? Right, so that is my causal question, and that is my estimand. That is the thing that I want to estimate. And so we can think about it like this, right? The estimand is this fancy cake that we want to make, this ideal. That's our estimand. And so here, our estimand might be the relative risk, the difference in risk of dementia if the entire population of age 45 adults started exercising 2.5 hours per week versus if that same population of adults did not do that and got no exercise. So that's our estimand. What is the difference in those risks? Our estimators are going to be G methods, right? So there's 3 basic classes of G method estimators, and we'll talk about those. And so it's the recipe for the cake that we want to make. The estimate is the numeric result that we get at the end of the day. And it may be vaguely similar to the estimand that we wanted to estimate, but at least we are clear on what we were trying to do, right? Our estimand is driving our analytic decisions because we're very clear about what it is that we are trying to estimate. So what are these G methods? There's 3 main estimators, as I mentioned. These are them. Inverse probability of treatment weighting and marginal structural models are probably the most commonly used G method, and probably you've encountered IPTW or some flavor of it, propensity scores, things like that. Standardization is another one, and this is implemented when we have large data sets with lots of covariates using the parametric G formula or G computation. And then there's another class of estimators called structural nested models. Now, one of the nice things about causal inference methods is that if you have specified your estimand and you make the same assumptions about the covariates and other various pieces of your analysis, you will get the same answer from all of these methods. And so it can be useful to use 2 or more of these methods to check and make sure that those are agreeing with each other. That can be a flag that something's wrong. But it is a nice feature, and I'll show you a little bit more about that here in a minute. So causal inference estimators are fundamentally different than regression, standard statistical regression. We use regression to implement these methods, but Regression is a stratification-based method. And one of the things that we tend to overlook is that this assumes that within all possible strata formed by the covariates and the treatment, the exposure outcome association is the same, right? You can include effect modification in your regression model of a couple of covariates, but that still assumes that with the levels of all of the other covariates that you have, the exposure outcome association is the same, and that's a strong assumption. Causal inference estimators are not making that assumption. They are focused on holding the entire distribution of population characteristics constant. So they're not looking within strata of the population. They're saying in the entire population, holding all of their distribution, right? Age, sex, gender, education, whatever it happens to be, that entire distribution, multivariate, is held constant, and we compare the average outcomes under different exposure scenarios, right? So we're getting to that idea of we have a causal effect if the entire population is treated, and at the same time, the entire population is untreated, and there's a difference in the average outcomes. So I'm going to talk a little bit about inverse probability of treatment weighting again, because that is the method that you will see probably most commonly in the literature, or you may have used it yourself. And so this addresses those unequal probabilities of treatment that I mentioned. Observations are weighted by their probability of receiving a particular level of treatment, and it's the one that they actually received. Unlike prediction modeling, our goal here, when we look at the output from our weighting model, when we're developing these weights, we don't care about the residuals or those other kinds of things. We really care about the theoretical set of variables in L. So again, observations after we have developed the propensity scores, which this 1 over this f of a given L. So usually that f, that function, is the probability, and we use logistic regression models to estimate the probability that a participant receives their own exposure given the covariates that we have identified in L. And that's the propensity, right? That's their propensity for the treatment that they actually received. And the inverse probability weight is simply the inverse of that quantity. The usual practice here is to perform weight stabilization, which is multiplying that inverse probability weight by the marginal probability of treatment. And this shrinks the range of our weights, and it really reduces the influence of extreme values of the weights. You don't want a situation, for example, where you have one person who's counting for 100 people, for example, when everybody else in the data set has a weight closer to, 1 or 2, something like that. So stabilization helps us, all things considered, reduces the range of the weights, and will also improve our estimation of the variance a little bit. So when we've obtained those weights from just, again, very simple logistic regression models, we get those probabilities of the treatment actually received, take the inverse, multiply by the marginal probability, and now we have these inverse probability of treatment weights. When we apply these weights, we are creating a pseudo population, we call it. And so in this pseudo population, every person is exposed and every person is unexposed. And so therefore, we have conditional independence between the probability of exposure and the covariates. Stabilization ensures that the pseudo population is about the same size as our original data rather than doubled, which is what we get if we just use the normal weights. So again, the key thing here is that we are creating this hypothetical population, again, where everybody has exposed and unexposed representation. So there's no link between being exposed and the covariate values anymore. So this sounds pretty good, I think, but we have to keep in mind that it's only valid if the assumptions hold. And so we have to assess carefully our identifiability conditions when we're using these methods in order to make causal inferences. So how do we assess these assumptions? It turns out to not be that easy, of course, right? So in order to assess consistency, for example, there's nothing in the data that will tell us that. This has to come from outside the data. So this is going to be based on our expert knowledge, the knowledge of our colleagues, what's in the literature. To assess exchangeability, we have tools within causal inference, directed acyclic graphs or DAGs, which you may have used or heard of, that will help us select the covariates in L, and it will give us the opportunity to be very clear about our assumptions about how all the variables in our study are related to each other. We can examine the distribution of the weights again for those extremes and make sure that everything seems okay. And really importantly, we want to examine the weighted data for balance. So, and sometimes people refer to propensity scores as balancing scores. Everything that goes into the propensity score model or that treatment model, those variables should be very close to balanced in the pseudo population, by which we mean the standardized mean difference in the pseudo population is, less than 1/10 of a standard deviation. And in addition, we assess positivity, again, not in the data, based on, not entirely in the data. We can look at some things, but we have to have knowledge outside the data. And that is a common refrain when we learn causal inference, that it's a lot about the story behind the data. We need to know other things than what is in our data set in order to apply these methods. The article that I have the reference for down here, cannot recommend it highly enough if you are interested in using inverse probability of treatment weights. And I have to emphasize that G methods are not magic, right? See this a lot, especially in grant applications, and people will want to say we're using this, and so that means that we have eliminated confounding and we can do this. Not so. Causal inference tells us what would have to be true in order for us to interpret our estimates as causal effects, but it does not make it so. So the underlying assumptions, again, those identifiability conditions are very strong, and they always have to be evaluated for plausibility. And I want to sort of end here with an example, a numeric example from this article from 2017, an introduction to G methods. So it talks about IPTW and standardization and those structural nested models. So they've simulated these data, and there's a little DAG for them here, but basically A0 and A1 are treatment indicators for antiretroviral treatment at particular times during follow-up. Z1 represents whether or not the viral load is high. And then Y is the outcome, which is white cell counts, CD4 counts, I'm sorry, measured. Okay, so we have two treatment times, we have a covariate, and then we have the outcome and the N, and these are simulated again. But what I want to show here is the very nice feature that I mentioned earlier. So they used a bunch of standard regression models, linear models, to try to estimate the treatment effect of those antiretroviral therapies on the CD4 count at the end of follow-up. And of course, because all of these models are specified differently, we get different estimates for beta 1. So our modeling choices make a big difference in the results that we get. For the G methods, we can see that that's not so. Once we have made those specific assumptions about our exposure, outcome, covariates, and L, it's just a matter of applying with the methods that we have. And you can see here that the estimates from the G formula are those, again, these potential outcomes. What would be the effect on CD4 count in the population if everyone were treated at time A0 and A1 versus no one in the population was treated at time A0 or A1? So it's very clear what our estimand is. It's very clear what our estimate means. And I think a bit easier to interpret in many ways than what we get from standard regression models. So if the assumptions are so strong and unrealistic, as I've mentioned, why would we use these methods? I think they increase rigor and reproducibility in observational research. You have to be very clear about what you're assuming and why. I didn't get to talk about it, but they do accommodate time varying confounding in a way that statistical regression models cannot. So if you have time varying confounding in your research area, you need to investigate these methods. And I would also just say that the assumptions of standard regression are also unrealistic. So you're not really saving yourself any trouble by avoiding these methods for that reason. But important limitations, of course, exist. Only some kinds of exposures are appropriate for these methods, those that we could assign in a randomized trial and expect SUTPA to hold. If that doesn't work, we shouldn't necessarily not use these methods, but we have to be very clear that we've violated the assumptions. And then the other thing to keep in mind is while this is increasingly common in epidemiology, and you may be seeing it in some other fields, these methods tend to remain poorly understood. And so there needs to be some work in my side of epidemiology and getting these out there and explaining what's going on, because I think they're very powerful and useful methods. And that is the end. And so now we have time for questions. Thank you so much for your attention.
Well, thank you, Erin. That was excellent. So we will open it up to questions. You can either submit your question through the chat, or if you're so inclined, feel free to unmute yourself and possibly do your video, and we'll have some more interaction than we typically do in a webinar. So feel free to go ahead. So Erin, I guess I'll start off with one question is,
Okay.
So if one wanted to start using causal inference, just in terms of, software and just how to do it, what would they do?
It is surprisingly easy to implement in terms of software. So the article that I mentioned about the introduction to G methods, one of the nice things about it is that it has the simulated data set and the SAS software that they wrote to analyze the data. And so you can go look at that and play with it. The textbook, What If, also has data sets, and then lots of code for lots of different software packages. So they have Stata code, they have SAS code, they have R. I think they have Python now too. And so there are templates out there to show you exactly what to do. There's more than a handful of tutorial papers out there, for example, for the parametric G formula. So once you sort of have your mind wrapped around the idea of potential outcomes and what these estimands are, I think it's very straightforward to be able to apply them to data. The longitudinal analyses are going to be much more complicated, but they can be done. So I think it's much more accessible and attainable than maybe you would expect. If you can fit a logistic regression model, a linear model, a Cox model, you can do this.
Excellent. Does anybody else have a question they'd like to ask? Again, you can feel free to submit it through the chat, or just unmute yourself and go ahead and ask if you'd like. In the interim, I just had kind of a follow-up question too to what I asked, is that so for a lot of individuals who come from the behavioral sciences, where mediation analysis is often used to infer causality, how would you say that these causal inference methods maybe how do they contrast with mediation analysis?
I wouldn't say that they necessarily contrast. It's part of causal inference. So this idea of causal intermediates, it's all there. The software that we use, for example, one of the software packages that we can use to create those directed acyclic graphs that I mentioned, DAGD, is so you can estimate the total causal effect or the direct effect, right? So there are mediated pathways and unmediated pathways, and it can help you decide whether to condition or not condition on certain things depending on what you're trying to estimate. And so it's just another critical piece of it. So it's a little bit different in terms of all of the assumptions probably that are underlying mediation analysis and the way that you're thinking of it. But fundamentally, I don't think it's so different. This idea of causal intermediates will block some of the effect of the exposure of interest. It's all the same.
Oh, thank you.
Sure.
Any other questions that we have for Dr. Abner?
It was so clear. Nobody has any questions.
Well, if there are no other questions, we'll go ahead and end the webinar. Erin, thank you so much for giving the talk today. Do appreciate it very much. Do we have a question from somebody?
Yes. Sorry. Hi, Dr.
Hello.
Thank you so much for your talk. It was really informative and really exciting stuff. In fact, me and my colleague were discussing this topic a while ago. So he found this double machine learning methods that also study. So we were curious what you think of those. Did you try them, or basically how do you find them?
Yeah, so machine learning is definitely becoming a bigger part of causal inference. And in particular, when you have less information about the covariates in L, people like to use it. And there are also other estimators that I didn't necessarily talk about, like the doubly robust estimator, which tends to use some machine learning. I think that the difficulty with machine learning is that it's not theory, that there's not this, like, this is the causal pathway that I think is happening. You're specifying in a DAG, this leads to this, and this is also a cause of this. And so there's definitely a place for it, but it is not a piece that I have yet incorporated in my use of causal inference methods.
Okay, thank you. Thank you for sharing.
Absolutely. Thank you for your question.
I have a question too for Dr. Abner. I don't know because I missed the beginning part of your talk. Did you talk about a little bit about in ADRD research, how is the causal inference being applied, or do you know any known study that have done that?
Yeah, so there's a group that has used causal inference more. If you know Maria Gleamore and her group, she's been a pioneer of some of these methods. So their group does some of this. My colleagues and students and trainees have started adopting inverse probability of treatment weighting. Some of the I think by and large, though, these methods have not completely made their way into ADRD research. And that makes sense to me for various reasons, partially because a lot of the exposures that we're interested in aren't necessarily lending themselves to this framework. But genetics, for example, is a place where we see causal inference with Mendelian randomization studies, which I didn't talk about. It's a little bit different, but that is primarily where you'll see, I think, at this point, causal inference used in our field.
What was the first group? What was the name? Would you mind saying the name again?
Oh, absolutely. Maria Gleamore, G-L-Y.
Okay.
Yeah.
Yeah, I know her. Okay.
Yeah, absolutely. Yeah. So she and her trainees have several papers where they've used some of these methods.
Thank you.
Yeah, absolutely. Thank you for your question.
All right. Well, Erin, thanks again for giving the talk today. I do appreciate it very much. The recording for this webinar will be made available soon. I will send out the link to it to all the registrants once it is uploaded. So thank you again to everybody and to Dr. Abner for your time today. And when we have the next webinar scheduled, I will send out notice and let everybody know about it. So thank you very much.
Great. Thank you, Mike. And thanks, everyone.
Thank you.